All right, today we're going to go ahead and go over a practice problem. And so the problem says two isomers have the same connectivity but different specific rotations of positive 15 degrees and negative 30 degrees respectively. What term can be used to describe this relationship? And so the first thing we want to do is actually kind of give a little background of some of these terms, right? And so isomers have two kinds. There are two categories, structural, or aka constitutional, and then the other kind is stereoisomers. Stereo means space, and so they're isomers with different spatial orientations. Now, structural isomers have different connectivities, but because they're still isomers of each other, they have the same molecular formula. So the term isomer means same formula, molecular formula. And then again, it was broken down into constitutional isomers or stereoisomers. Stereoisomers have different connectivity. So, constitutional isomers have different connectivity. So, if we're looking at this problem and we're reading it, it says they have the same connectivity. So, immediately, we know that they're isomers, but they have different connectivity. Here is structural, constitutional. So, C is ruled out because constitutional isomers have different connectivity, right? And so we're left with stereoisomers. There's two types. We have geometric and then we have spatial. And so geometric would be cis versus trans, and it refers specifically to double bonds. So it's trans across this axis, or cis across this axis, meaning they are on the same side of that axis, versus trans, which means they are on opposite sides of that axis. So that would be geometric. Spatial, we would have enantiomers and diastereomers. So enantiomers are non-superimposable mirror images. Mirror images of one another. Diastereomers, the di in diastereomers refers that there's multiple stereocenters. Enantiomers don't necessarily have to have multiple stereocenters. They just have to be non-superimposable mirror images. But diastereomers have to have multiple stereocenters, and those stereocenters, at least one of them is different and one of them is the same, right? And so let's go back. So these are non-superimposable. Diastereomers are non-superimposable. Non-mirror images. Oops. Now, let's go back and look at the problem. It's telling us we have a specific rotations of positive 15 degrees and negative 30 degrees. So that's the other clue here. If we have something called a racemic mixture, what we have is two molecules that are enantiomers of each other, so enantiomer A and then B, And this one would rotate this molecule, they're enantiomers. So they're non-superimposable enantiomers, non-superimposable mirror images. And so this optical activity of enantiomer A versus enantiomer B is going to be the same magnitude but opposite direction. So the magnitude would be 30 for each, but opposite direction. So what does that mean? So that means when I put polarized light on these molecules, what's going to happen is one enantiomer is going to rotate it one direction in the magnitude of 30, and the other enantiomer is going to rotate it in the opposite direction in the magnitude of negative 30. Now, racemic, by definition, means you have 50% of this and 50% of the other enantiomer. And so because there's 50-50, they cancel out. So the optical rotation would be 0 degrees. The positive 30, 50% of it would cancel out the negative 30, 50% of the solution. So you have 0 degrees. So if we look at our problem, we have two different specific rotations. So can that be our racemic mixture? No. Why? Because 15 degrees is not the same magnitude as negative 30 degrees. So it's not going to be 50-50 of enantiomers. So racemic mixture, the definition has to be enantiomers and it has to be in 50-50%. Or 50-50 proportion, right? So half of A and then half of B, which would ultimately give you 0 degrees. So there are three defining features of enantiomer or racemic mixtures. They're enantiomers, they're 50-50, and they total out to be 0 degrees. So what we have here is positive 15 degrees and negative 30 degrees. So are they enantiomers? No, because if they were enantiomers, you would see positive 30 and negative 30, or positive 15 and negative 15. Same magnitude. So we'll do enantiomers here. Would have the same magnitude. Optical rotation. But have different directions. No, sorry, excuse me. More specifically, they have opposite directions. So what does that mean? That means positive 30 and negative 30, for example. Okay, so enantiomers. So here we clearly don't have enantiomers. We clearly don't have racemic mixtures. And so lastly on our list is diastereomers and conformational isomers. Now, conformational isomers are actually the same molecule, but something, a bond, say a bond, oops, a C carbon, a CC bond is rotated in one versus the other. So if I give you an example, this molecule is exactly the same as this molecule, But what I've done is I've rotated this carbon-carbon bond. So what happened is that OH went to the back, this H went down, and that H went over there. So if I redraw that, let's say this is HA, this is HB, and that's the OH. HA went there, HB is now in plane, and then the OH circled back around. So they're the same exact molecule, right? But there's a rotation across the CC bond. This right here is that rotation. And so when you have the optical activity of a conformational isomer, it's just going to be one number. It's not going to be two, right? Because they're the same molecule. So they're not going to have two different rotations. Whereas enantiomers are non-superimposable mirror images, but their structures, because they're mirror images, are not the same. Their connectivity is the same, but spatially they're different. So they affect polarized light differently, giving us two different angles, positive 30 and negative 30. Now, distereomers lastly, we said they were non-superimposable, non-mirror images. Okay, so that's here. And so what that means is they're going to have different directions of rotation and different magnitudes. All right, so let's go back here and go through diastereomers. So what do we have here? Positive 15 degrees, negative 30 degrees. That means they're different directions of rotation, positive and negative, different magnitudes. And so our correct answer is diastereomers. Conformational isomers are incorrect because, again, they would not give us two different rotations. It would be just one optical rotation in one direction or the other, but not two different directions. And so to quickly recap, if we're given the same connectivity, that rules out constitutional isomers. C is out. If they are differing magnitudes and directions, it means diastereomers. And then if we have conformational isomers is ruled out because, again, there's only one optical activity in one direction. So let's just say it would be positive 30 and that's it. There would be no second specific rotation. And then racemic mixtures, its overall mixture would be 0. Each one would be positive and negative 30 in different directions and in opposite directions. And there would need to be 50-50 in terms of that ratio.